students, welcome to this lecture on the subject of advanced semiconductor devices KEC 056. This is lecture number 3. I am Dr. Raman Kapoor, Associate Professor at ABS Engineering College, Ghaziabad. In today's lecture, we are going to start a topic which is related to carrier concentration in semiconductors at thermal equilibrium. Okay. So, let us start. In our previous lecture, we had concluded at the energy band theory or formation of energy bands inside semiconductors. We had seen that you can mathematically obtain a graph between energy and wave vector k, which is proportional to momentum, your so called EK diagrams. Okay. When you mathematically solve the Schrodinger equation for each of those valence electrons inside an atom which share their potential well with each other, you get a graph in such a way that you have allowed levels of discrete energy levels closely spaced called an energy band. Okay. And not all the energies are allowed, and some of the energy levels are considered to be forbidden. This leads us to the origin of energy band gap. Okay. Now, taking that as the basis, you can now differentiate between different materials in terms of their conductivity on the basis of their energy band diagram. Okay. This energy band diagram or the energy gap is decided by how tightly bound the electrons are inside a solid. Okay. Inside a metal which is considered to be highly conductive, as we know, this energy band gap E g is actually 0. So, you can say that the valence band and the conduction band actually overlap with each other, and the electron by itself you can't say that it is belonging to valence band or it is belonging to conduction band. Okay. So, if energy band gap is 0, we are looking at a metal where there are a lot of free electrons available, because here you can see that electrons are already available in the conduction band and they can come to the conduction band or go back freely. So, that is why they are known as free electrons. Okay. If this energy band gap is at a certain intermediate level, say limited to 1.5 to 2 electron volt, from 0 to up to 2 electron volt, we say that the amount of energy required for any electron to jump from valence to conduction band is finite but manageable, but a small level of energy is required for electrons to jump from valence to conduction band, and once they reach conduction band they become free and they start to contribute towards current. Okay. This is for semiconductors, but if this gap is quite wide, okay, if this gap exceeds 2 electron volt, now that is something of a standard value we would say, but it is not a hard rule that anything above 2 electron volt will be an insulator only. You can have wide band gap semiconductors also where E g is higher than 2 electron volt, but just for the sake of discussion you can say that when E g is a very high value, then a lot of energy is required for electrons to jump from valence to conduction band, and this kind of a material we refer to as an insulator. So, this conduction band is largely empty in case of a insulator. Okay. Now, the energy gap is also temperature dependent, right. Now, we would not go into that much of detail, but our main aim is to study the differentiation of these materials on the basis of their energy band diagram. So, if you see this band structure here, these blue dots actually resemble electrons and the hollow circles represents the atoms. So, you can say that the electrons and atoms are intermixed with each other, and you can't say that a particular electron belongs to a particular atom. So, they are freely available. While in the case of a semiconductor, you would say something like of a covalent bonding, where a finite amount of energy is required to, suppose if you want to release an electron from the bond and make it available for conduction. Okay. So, the finite amount of energy is required, that is why we say that the energy band gap is a small but finite value. Okay. So, this is the differentiation between different types of materials. Let us see what happens when we reach what is known as thermal equilibrium. Okay. We first start with an intrinsic semiconductor, which is nothing but a pure material. The semiconductor or the silicon which is used for fabricating electronic devices, it is usually fabricated, these devices are usually fabricated under a highly pure environment, where the wafer on which the semiconducting wafer on which devices are manufactured, that is considered to be free from any impurities. Okay. And we have not added any impurities by ourselves also, which we will see later on, which we can do. Okay. So, we refer to the case of intrinsic semiconductor or the pure semiconductor. Thermal equilibrium basically implies that the material is kept in the dark. We have not applied any biasing. Okay. So, no electrical voltage has been applied. The only source of energy is the thermal energy. So, at room temperature, this thermal energy, which is K times T, K is your Boltzmann constant and T is temperature. When we say room temperature, we are referring to around 300 Kelvin. So, this energy comes out to be around 26 milli electron volt. Okay. If you use the value of Boltzmann constant in electron volt per Kelvin, okay, which is around somewhere around 8.6 into 10 to the power minus 5 electron volt per Kelvin, this is the amount of thermal energy available to the charge carriers inside a pure semiconductor. With this energy, when electrons get excited by thermal energy, they jump to the conduction band, okay, and it leaves behind a vacancy which is known as a hole. Semiconductors are considered to be generally considered to be bipolar. So, you have both two types of charge carriers, electrons as well as holes. Hole is nothing but an absence of an electron. So, when these electrons, when they jump to the conduction band, what they leave behind is an open bond or a vacancy which they can again refill, okay. And this vacancy is known as hole, and it is considered as a positive version of the electron. It is also referred to as a charge carrier. Okay. So, the number of free carriers per unit volume available for conduction at thermal equilibrium in intrinsic silicon is known as its intrinsic carrier concentration. Okay. So, when we refer to carrier concentration, which is the broad topic of this lecture, carrier concentration refers to how many charge carriers. Now, they can be electrons, they can be holes, both. So, the number of carriers which are available per unit volume. Okay. And if you are referring to electrons, we are interested in how many electrons are there in the conduction band, and when we talk about holes, we are interested in how many holes are there in the valence band. Okay. So, here we define these symbols also. EV is your valence band maxima or the top of the valence band. This is the highest energy which electrons or holes can occupy inside the valence band. EC refers to the minima of conduction band. This is basically the start of the conduction band. This is the minimum energy level which electrons can occupy inside the conduction band, and EG is basically the difference between EC and EV and refers to as the forbidden energy gap, right. These are some of the introductory symbols I am introducing now. N in lower case represents electron concentration. Now, see, this is not the absolute number. When we refer to concentration, we mean numbers per unit volume. So, N means number of electrons in the conduction band, that is above EC, per unit volume. Okay. And when we say P in lower case, we are referring to number of holes per unit volume inside the valence band. These are the ones, electrons in the conduction band and holes in the valence band. These are the ones which actually contribute to current in a semiconductor device. At thermal equilibrium, N is equal to P in a intrinsic semiconductor. Okay. So, that pure semiconductor which is free from any kind of impurities, the number of electrons which reached from valence to conduction band, they leave equal amount of holes behind. Okay. So, N is always equal to P inside an intrinsic semiconductor at thermal equilibrium. Okay. So, this is the start of our topic on carrier concentration. Let us proceed further. Okay. See, one of the most important properties of any semiconductor or any electronic device, in the introductory lecture I had said that when we talk about electronic devices, we are actually referring to semiconducting devices, okay, because the active material inside these electronic devices is a semiconducting material. The major objective of these devices is to produce a lot of current, and for that, instead of using a pure or an intrinsic semiconductor, you can introduce a lot of amount of doping, which is a deliberate addition of impurity atoms. Now, by impurity atoms we do not say we mean that those which are not from the same group of the periodic table. So, if you are doping silicon, you can dope with group 3 elements, the so called trivalent atoms, or with group 5 elements of the pentavalent atoms. These are known as dopants or impurities. This enhances the conductivity. Okay. So, you can tune the conductivity of a semiconducting material via doping. When these impurities are ionized, so when they basically increase the carrier concentration, we say that the carriers are depleted, they leave behind a charge density that results in an electric field and sometimes a potential barrier also inside a semiconductor. Okay. Going forward, in intrinsic silicon, that is without any impurities, the general structure is of covalent bonding via tetrahedron, where each silicon atom shares its 4 valence electrons with 4 neighboring atoms. Okay. If this intrinsic silicon is doped with say a material which has 5 valence electrons, so silicon has 4 valence electrons, you add another atom which has 5 valence electrons, okay, like phosphorus or arsenic, these are your group 5 elements. So, out of these 5, 4 of the electrons can bond with silicon and form a covalent bond. So, 4 valence electrons of silicon, 4 of phosphorus, and they make a covalent bonding, and then you have 1 electron left, okay, which is not bonded with anyone. Now, that is considered to be basically free. Okay. So, this pentavalent impurity basically donates an electron. So, one atom, one dopant atom which is pentavalent can donate 1 electron. Because it is donating an electron, it is also called a donor. Similarly, if you dope with trivalent impurities, okay, any element which has 3 valence electrons like boron, right. So, those 3 valence electrons can bond with 3 valence electrons of silicon, and then the 4th valence electron of silicon is left, and if that leaves the valence band, it leaves behind holes. Okay. So, that trivalent impurity which you have added has a capability of accepting that 4th valence electron of silicon. That is why it is known as a acceptor ion or acceptor impurity, right. So, this is how the bond structure of an intrinsic or a pure silicon looks like without any doping. You will have the silicon atom at the center and 4 valence electrons bonding in a 3-dimensional repeated structure. When you add pentavalent impurities, you actually add an extra electron, and when you add p type impurities, the trivalent impurities, you actually accept one, the impurity accepts 1 electron. So, it adds a hole. Okay. So, when an electron is accepted by the acceptor impurity, we say that a hole is donated. Okay. So, this is what the concept of doping is. It is generally done to enhance the conductivity of the semiconductor. Okay. Now, we come to the main topic, which is carrier concentration, right. So, any semiconductor device has a primary aim of generating current. It should be able to produce appreciable amount of current for minimal levels of applied voltage. Okay. We are interested in how fast the carriers move inside a semiconductor. So, the speed and momentum is important, but at the same time how many carriers are actually present is also important. Why is it important? See, what does carrier concentration means? It means number of charge carriers per unit volume. If we are talking about n type semiconductors, we are interested in how many electrons per unit volume are there in the conduction band. For p type, how many holes are there per unit volume in the valence band. It is these 2 types of charge carriers, electrons in the conduction band and holes in the valence band, which actually contribute to current. So, if you have higher concentration, higher charge carriers per unit volume, you would have higher amount of charge available to you, and since current is directly related to charge, you will have higher current density also, right. So, our objective is we want to calculate how many electrons per unit volume are there in conduction band. Okay. Here Cb stands for conduction band and here Vb stands for valence band. So, I need an expression where I can say that okay, these many electrons I have available with me per unit volume inside conduction band. So, these can contribute to current. These many holes are available in valence band per unit volume. So, these can contribute to hole current. Okay. So, that is our main objective. We need some expression so that we can quantify the number of charge carriers which are available per unit volume. Okay. And if we want to calculate this carrier concentration, we need 2 parameters. Okay. To obtain the expression for carrier concentration, you need two parameters. Number one is what is known as density of states. Okay. When we say state, we need states mean the energy level. Okay. When we say what is density of state, state means an energy level which can be occupied by an electron. And where do we get these energy level? By solving Schrodinger equation for the potential well formed by each atom. Okay. So, these states, these energy level which an electron can occupy, that is what is meant by state. Density of states is defined as how many energy states are available per unit energy per unit volume. Okay. So, if I have conduction band start of from EC, so this is your conduction band, and if I write for EV anything below, this is my valence band. Okay. So, in each of these bands, how many energy states are available per unit energy per unit volume, how many of these states which electrons can occupy. Okay. This is referred to as density of states. Second parameter which we need is, once you know how many states are available, then you want to know what is the probability that a particular state is occupied or not. Okay. This is given by the Fermi-Dirac function. We are going to study that in more detail later on. Okay. So, I need two things. I need how many energy levels per unit volume per unit energy are available. Second, I need what is the probability that a particular energy state whose energy is E, any energy E is actually occupied. These two things are going to help me to calculate the carrier concentration. Okay. So, just to see what density of state is, I will just give a quick overview. I have already given the definition. So, in the conduction band, this density of state is represented by G subscript C, C for conduction band. It is a function of energy, okay, and this is the mathematical expression for it. Okay. In the valence band, density of state is represented by G subscript V, V for valence band. Again it is a function of energy, right, and this is the mathematical expression. This M, Mn star, Mp star, these are the electron and hole effective masses. Now, effective mass concept which we have covered in the last lecture, okay, that is the mass experienced by a charge carrier inside a 3D crystal. Okay. EC, as you know, is the conduction band minima, EV is valence band maxima, and H here is Planck's constant. Okay. If you see these two equations, you would see that the density of states is actually proportional to square root of E. Okay. And in conduction band, we are referring to all those energies above EC, and in valence band we are interested in all those energies which are below EV. Okay. Because EV is the maximum energy in valence band, EC is the minimum energy in conduction band. So, we are interested in all those energies which are EC, which are above EC in conduction band, and for valence band we are interested in all those energies which are below EV. Okay. So, you can see that if this is your EC and EV on the energy scale, the number of energy states take a parabolic path and they increase, okay, as this difference increases. Okay. So, this way more and more states are available on the higher side, more and more states tend to be available on the lower side in valence band. Okay. So, this is the graph, this is the distribution of density of state. These are the energy states which electrons can occupy, these are the ones which are available per unit energy per unit volume. Okay. The second thing which we needed was the probability given by the Fermi-Dirac function. Now, this is not a density function, this is the absolute probability, okay, quantified absolute probability that a particular energy state is occupied or not, and it is given by 1 plus exponential of E minus EF over kT. Okay. So, this is, if this is the energy scale and this is f of E, this function here is given here f of E. Okay. You can see that as temperature increases, the probability also tends to increase. Okay. So, this is the distribution of this probability function with respect to energy. So, I need two things, I need density of states and I need the probability occupancy. These two I combine together and I want to get the expression for carrier concentration. Okay. So, let us see how we do it. First, the electron concentration, what did this means? Number of electrons per unit volume in the conduction band. Okay. This is I am trying to derive an expression for. By definition, this n is integrated on the energy scale from E c till plus infinity, because E c is the minima of conduction band and it goes up to plus infinity. Okay. From E c to plus infinity, G c is the density of states, number of states per unit energy per unit volume, multiplied by the probability that a particular energy state E is occupied or not, okay, times d E. So, now you can see that G c times d E is going to give you number of states per unit volume, and when you multiply by the probability you get number of charge carriers per unit volume. Okay. So, this is how basically you obtain the density of the carrier concentration for electrons in the conduction band. Okay. If I write the expression for G c here, which I have written on some of the previous slides, and the Fermi-Dirac function for electrons, if I integrate this, this is the expression which I am going to get for the carrier concentration. Okay. So, let us just quickly see how we arrive at this function. Okay. Now, n is given by from E c till infinity. Okay. And if you see this expression here, it is 4 pi to square root of E minus E c into, now see this probability here, okay, this just this part here, okay. This is 1 by 1 plus exponential of e to the power exponential of E minus E f over k t. Now, I am referring to those energies which are on the higher scale, which are positive, which are higher above than E f, which basically means that E minus E f is going to be a large positive number. So, this 1 I can ignore, okay. This 1 I can ignore. So, I can write here as e to the power E minus E f over k t dot d E. This expression I want to integrate. For this I use the substitution method. I am going to define a particular variable eta, which is equal to E minus E c over k t. Okay. And this basically implies that d E is going to be k t times d eta. Okay. So, I have a substitution for E minus E c, I have a substitution for d E. Okay. And if I want to substitute E minus E f, I can say that E minus E c from this expression is equal to eta times k t. From this I can write E minus E f plus E f minus E c is equal to k t times eta. Okay. So, now I can substitute E minus E f also, I can substitute d E and I can substitute E minus E c in this integral. Okay. So, if on substitution I am going to get an expression something like, so I have 4 pi into square root of k t into k t, okay. And then I am going to have e to the power of minus of E c minus E f over k t, and the integral is only going to have, now the limits, if you see initially the limits were E c. So, if I put E equal to E c, eta will be 0, if I put E equal to infinity, eta will be infinity. So, my limits are going to change from 0 to infinity, and I am going to be left with a function where I will have eta into e to the power minus eta. Okay. This you can also do yourself. I have given you all the expression for substitution, right. When you substitute all this in this integral, you are going to get a term something like this. I can combine all these terms together which are common. This is a standard integral whose value is actually going to be equal to 1 by 2 root pi. Okay. With this, finally, I will get this expression 2 into 2 pi effective mass k dot t by h square, okay, into e to the power minus of E c minus E f by k t. Okay. And this term which is written over here, this is commonly referred to as N c, which is effective density of state in conduction band. Okay. So, I am going to get the expression for carrier concentration n equal to N c minus E c minus E f over k t. Okay. So, this is the expression for the electron concentration in the conduction band. For the holes, the approach is exactly similar. You would use the density of state in the valence band. The limits are going to be minus infinity to E v, because E v is the top of the valence band. Okay. Plus, instead of electron probability, I am using the hole probability, because I am calculating hole concentration per unit volume, right. So, I am going to use, instead of f of e, I am going to use 1 minus f of e. You put the expressions here, right, and the 1, if f of e was equal to 1 by 1 plus e to the power e minus E f by k t. Okay. So, 1 minus of this is going to be this expression. Here, if you see this exponential here, e minus E f is going to be a negative number, which means the exponential can be ignored with respect to 1. Okay. So, if I want to derive the expression for p, it is going to be 4 effective mass, okay, exponential of E minus E f by k t, and the limits are going to change from, if you put minus infinity here, okay, the limits are going to change from minus infinity, same here. Okay. Integrating this expression with the same case, you are going to get the expression for holes, which is this expression, where N v is the effective density of states in the valence band. Okay. So, with this we have derived the expression for N and P, electron and hole concentration, which is the carrier concentration, number of charge carriers per unit volume inside the conduction and the valence band. Okay. So, we will continue our discussion on carrier concentration in our next lecture. Thank you.